Hi folks. Today I wanted to cover something relatively straightforward, but that's actually pretty useful in a lot of workflows, but isn't necessarily built into Houdini. And that's the ability to break glue constraints with something other than impacts. So by default, when you're doing rigid body simulations and you're using glue, the only way to break glue is when something smacks into it. But often what we want to do is break our do our destruction using other forces, in particular arbitrary forces, quite literally. So maybe we have an explosive force, we have a metaball force, we have a curve, we want to sort of draw things, we have a suction force, we have fluid forces. We have all sorts of things that we want to be able to apply and use in our destruction, but by default, glue doesn't pay attention to any of those things. So I just wanted to do a relatively quick, relatively straightforward tutorial today to cover one way that you can sort of port over arbitrary forces and use them to break your glue so that you can still get all of the nice fast benefits of glue instead of something like soft constraints, which you could use instead but are really computationally expensive. So we want to be able to keep glue but still get more arbitrary and more sort of good control over how we break it. Okay, let's get started. I'm going to drop down a geometry node and I'll just call this force break. And we'll dive inside, and the first thing that we're going to want to do is give ourselves something to break, some interesting geometry to work with. So I'm just going to build a very basic I hesitate to call it a building, but something building-esque. So it's going to have sort of walls and floors, and that'll be pretty much all we'll deal with. So let's just give this kind of an interesting shape here. Maybe something like this. This is roughly sort of a building kind of a shape. Maybe we can make it a little bit wider, a little bit taller, resting on the ground. That looks pretty good to me. Now, to turn this into sort of a shell, I'm going to do a few Boolean operations here. I'm going to grab a bound first. I like doing this because if you just transform the box, you need to worry about the pivot, and especially for doing things like buildings, I want sort of shells all around every edge, but actually not at the bottom. And since I'm doing a Boolean, I want it to sort of overlap at the bottom. So you'll see what I mean, but the bound box can be really nice for boxes, at least, because you have all of these independent paddings. So what I want to do is just give negative paddings for all of these. And so that's going to pull it in from each of these edges by the same amount. But I actually want to give it a bit of a positive padding on the bottom, just to sort of punch it out through the bottom. So I kind of like this setup because you can do that pretty easily. And then at that point, we just do a Boolean subtract. And we get ourselves a little shell. So that's great, that's a good start. Let's just put some floors in here. Again, I'm going to do this in a really sort of straightforward way. I'm going to start with a grid. Let's just make sure it's big enough on every side. That's totally fine. I'm going to poly extrude this by that same sort of offset by 0.1. We'll do that. And I'm going to make sure to output the back. I want that to be solid. So without that, it's not. And then we'll just do a copy transform to give ourselves a variety of different floors. So I'm not sure quite how high these should be. Let's say it went up by 1. That's maybe a bit too much. Let's try 0.75. And then we can sort of bump these up till we're filling that a little bit more. Maybe I'm just sort of trying to dial this in so it's got a relatively evenly spaced arrangement. That looks pretty good to me. So now I'm just going to take this bound again, and I'm going to do a Boolean intersect with all of these. And that'll give me my floors, and they'll be nice and sort of set inside here. So if I just merge all of this stuff together here, we get what we can very generously call a building. So let's just call this building, quote unquote. And this is just to give myself kind of an interesting shape to work with. I like to have interior cavities when I'm doing destruction to just destroy sort of a solid block. You rarely get very interesting sort of looks from that. Okay, so with this in place, let's go ahead and just fracture this. So I'm going to take, I'll just take my original box here. I'm going to do an ISO offset, give it a little more resolution to get some fog here. And my display is already up to its old tricks, so let's see, there we go. And let's just scatter a good number of pieces. Let's do something like 1500. This will be a relatively sort of lightweight fracture, but it'll be enough to see what we're working with here. Now, because I have multiple pieces here in this geometry, this isn't just one chunk, you can just do a Voronoi fracture on this kind of compound geometry, but I find often it'll give you trouble, so I prefer to just go for each piece in here. So we have several different pieces, we have each of the floors, and then we have that shell, and we'll just do the fracture for all of those. Or for each of them, I should say. So for each of those, we'll just fracture based on the same points, so we'll have the overall same sort of fracturing going on. We'll just do all of them. And one thing to note here, this Voronoi fracture, it doesn't know about the previous one, so it's just going to start at piece 0 every time for each individual piece. So we're going to have multiple sort of connected piece zeros. So we just want to rename this stuff. So I'll drop a connectivity node, I'll put that on primitives, and just drop a prim wrangle and say that our name, we'll use sprintf, should be name, %d for an integer, and we'll just grab that class attribute. So now, if we looked, say, here, and we see names, there's sort of 1,028 unique names. If we look here, we see, okay, it's actually 1698. And so those were just some of those duplicate pieces. So now that's taken care of. So this is our base fractured geometry. And on the geometry side, all we really need to do here now is just assemble this. We don't want to create a name attribute, we already have one. We will create packed geometry. So there we get our 1700 packed pieces. And the last thing I want to do is just sort of make the lowest ones inactive. So I'll do that with a group. I'm going to call this group anchor. And I'm going to do, this should be on points, and I'm going to go keep inbounding regions. I'll just get the gizmo here, and really what I want to make sure I get sort of all the way front and back, and then I just want the handful of pieces nearest to the ground. This is just to make sure it doesn't sort of fall over if anything starts to influence it, so all these pieces will be stuck to the ground, and that should be just fine. With that group in place, I'll just do an attribute create here. This attribute will be called active, it's on points, it should be an integer, and the default I'll say is 1, but the value for this group I just made, anchor, will be 0. So that means most of the pieces, all the ones not in this group, are going to be active, they'll simulate, and then just this set that we selected here is going to get the value of 0, so it won't be active. So there's our geometry. Now for our constraints, for two reasons we need to process this a little bit more. We can't just take this output. We could have taken it for each piece, but then the pieces wouldn't be glued together. So ultimately we can't really use those constraints, so we have to go back to the old-fashioned version. So we'll just do a connect adjacent pieces, and I'm going to do adjacent from surface points. And right now it's got a max connections of 1. That's not really enough. Each of these individual pieces is going to be next to a whole bunch of other pieces. Let's see if I can get my display to behave again. There we go. Each of these pieces is going to be next to a whole bunch of other pieces. We want them all sort of nicely connected together. This isn't so bad, but I do want to sort of bump that up. Let's say at least 4, maybe even 6 or so. And that should be fine. That still just gives us, 14,000. So that won't be very heavy, and that makes sure everything is sort of nicely attached together. Now at this point, we could just give it a constraint name. We could just say this is glue, and this isn't really necessary for glue, but I'm going to do it here anyway. I'm going to say the constraint type is all. This is whether or not it constrains rotation as well as position or just position. And for glue, that's sort of not, it doesn't apply. The reason I like to put this in here is just as sort of a reminder to myself to always basically worry about this, because every other constraint this is actually relevant. So glue is kind of the exception where you don't really care about setting this, but I like to set it just to keep it in mind. And also if I happen to change the constraint type in some sort of SOP solver or some other portion there, this is already taken care of. So you don't actually need this right here, but I'm going to keep it. That reminds me, we are going to want our rest length here, so I'm just going to put that on there. And the last thing we might want to do is just say, let's set our strength. And I'm just going to set it to 1 for now so that we can set it up inside the network. And let's just go ahead and call this con for constraints. Now I'm going to want to change this network a little bit, make it a little bit more interesting. Right now there's no chunking, everything is going to be sort of equal strength, but just to get us started, let's sort of throw that in there. So now we can set up our DOP network. It's going to be a very sort of straightforward RBD network. I'm going to get a ground plane. I'm going to get some gravity. Oops, that's not gravity. That's gravity. I'm going to alt drag these two to get a merge. I'm going to turn off the display of the ground plane because I never want to see it. Drop a rigid body solver, a constraint network, a packed object, and a glue constraint. Okay. So for our constraints, we'll just point to that con null. For our geometry, we'll just point to our geometry null. And for our glue constraint, we'll say our constraint is glue. Now, if we were to run this right now, it shouldn't really do anything. It's only acting under gravity, and that won't be enough to sort of give it any kind of change. So it will just sit here. If we were to throw anything in here, right now the strength is reasonably high, actually. It probably would hold together. So this is a reasonable place to start for us, actually. Now, what I want to sort of show you here is that if we were to throw some kind of a force on here, let's just grab a pop force, and we'll just stick that in the post solve, and we'll say, let's give it a good gust in the x direction, and a little bit of noise there. If I were to add this force, if I run this, and we look at the geometry here, you can see that, sure enough, it is creating this force attribute. It is applying this, it's putting this on the points, and they are experiencing fairly strong forces. You know, these forces are a lot stronger than gravity even. And our strongest force is up here at like 88. Now, part of this actually is, where do we have this ignore mass? Ironically, when you check ignore mass, what it does is incorporate mass into it. So a force of 10 units, I assume these are newtons, a force of 10 units on two objects is going to sort of change. It's going to give different accelerations if they have different masses. What ignore mass does is says, well, let's take into account their mass, and we'll basically multiply the force to sort of make it equivalent. So a heavy object should accelerate as much as a light object, is what this is saying. So ironically, if you check ignore mass, what it's going to do is incorporate the mass into the force. So that's why we're seeing these forces. So if I take the noise out of here, you'll see that the force, and if we go over, let's just look at these two things, force and mass, you'll see that the force is 10 times, so that's our sort of unit base force, 10 times the mass. So when the mass is 1.5, the force becomes 15. So if we go to that maximum, it was sort of in the neighborhood of 80. That's because that thing was our heaviest chunk here. So first of all, when we're dealing with sort of trying to use force to disrupt these pieces, we actually want to make sure that we're not ignoring mass. And in that case, the force just becomes the force. So it doesn't take into account the mass. We're going to take into account mass when we're actually seeing what it ought to do. So I like to keep this in sort of its standard units so that we can then take care of mass on our own. Okay, so the main thing that's important here, though, even if we crank this up to sort of a ludicrous value, it's not going to do anything. So glue is really nice. It's a really good constraint because it makes things nice and cheap. Because what glue lets you do is say, well, as long as these items are attached together, I can treat them all as a single rigid piece. And that makes these constraints really powerful because they're really cheap. The solver can basically simplify its calculations quite a lot. Now, the problem is it can't really respond to differential forces on its individual pieces. What glue constraints respond to are impacts. So when something gets hit, that impact basically has a quantity, and that impact is distributed to nearby links based on this propagation duration and propagation rate, and it decays based on this half-life. So if it gets hit a whole bunch by light taps, this may build up enough, especially if you increase this half-life. This is how many seconds it takes for that sort of impact value to decay. But basically, all it responds to is stuff hitting it. It responds to collisions. It doesn't know about force. It doesn't know about wind. It doesn't know about any of those things. So glue can only really be broken by default by force. Now you might think, okay, well, we can just do this with like our new bullet soft constraints. So if I just say this is glue now, pipe that in here instead. This will obviously be plenty. If I just go to 10, you'll see now it's going to simulate slowly, but it is actually responding. And so you could do this whole approach with soft constraints. The problem is soft constraints are a lot more expensive. It's actually looking at each individual constraint between each point on each time step, and it doesn't matter if they're still attached. They can still move independently, which gives them different strains, and all of this gets a lot more complex. So if you want your sort of destruction to respond to things like forces, arbitrary forces, you could go sort of a soft constraint route, and you could basically just make it more and more stiff until it seems basically like a glue constraint, but that's going to get really expensive. You don't really want to do that. So instead what we want to do is keep our old-fashioned glue constraints, our nice cheap glue constraints, but somehow pay attention to force. So instead of only breaking based on impacts, we also want it to break based on these forces. And it turns out that's not such a difficult thing to do. Basically what we're going to do is we're going to take this whole glue concept of impacts. We're going to include our half-life, our propagation iterations. We're going to sort of incorporate all of that stuff. And instead of looking at impacts, we're actually going to look at displacement due to forces. So predictably, we're going to use a SOP solver here. I'm just going to plug this right in here. And the first thing we want to do is sort of bring over these forces. So again, if we play forward here, we get force on these points. We want to bring that into our network here. So to do that, I'm just going to actually import the geometry from this same DOP network. So that's from this network, it's the RBD object, and I just want to grab that geometry. So there it is, and sure enough, if we scroll over and look at force, there's our force. So we've got those values. So now we want to copy this over onto our constraints. So I'm just going to do an attribute wrangle here. Oops. And the first thing we want to do is line them up. So at the beginning, on the very first step, this should have, 16 or 1700 points. This has 1700 points. They're ranging from piece 0 to piece whatever. So you should think, well, maybe we can just use PT num. But if we're going to start breaking these constraints, that means some of these points are actually going to disappear. We're going to change the ordering. So after our first time step, kind of all bets are off. So we need to match this explicitly. So we'll grab our matching point using find attrib val, and we want to find the match from that stream 1. It's going to be a point attribute, and it's the attribute called name, and we want to match it to the name that's on these points. So these points on the primitives for our constraints. Well, this thing is clearly confused because this stuff should not be on those constraints, and it probably isn't. Let's just go back to our constraints. Sure enough, there shouldn't be much of anything there. Let's just go in here again. Well, it seems very confused about what it's showing me. That's okay. Here we go. Okay, so these constraints have a name attribute, and this stuff on the geometry has that same name attribute on the point. So we just want to match those. So we're going to compare those, and that'll give us the matching point from this stream. Then we're just going to say our force is just the force from that stream from the matching point, and I want to bring over the mass as well. We could just do this mass transfer on the very, very first step, and in fact, just for the sake of argument, let's do that. We'll just find this matching point, pull that in here, and actually we're just going to say yeah. Well, we could do this. No, I'm not going to do this. It's just not worth it. It's going to have to do this conditional every time anyway, and then, yeah. The expensive part, honestly, is this match. The rest of it is just read calls, so we're not really gaining anything. The idea is that mass is never going to change, force is going to change, so we don't really need to read mass every time. But it's not really costing us anything. The overhead is on finding this matching point. So this extra little read here is not really going to break the bank. So let's just leave that in there. So now, on our constraint points, we have our force value and our mass value. And you'll see that force is 0 here. That's just because we're on this very first frame, and this SOP solver is being executed before this is. I'm not sure if we put this on the pre-solve, if that would come through. Nah. Yeah. This is one of those funny things about the constraints being in their own network. This is why you could do the attach internal constraints to objects, which we could do in this case, and then we could have a little bit more control over when this gets executed. But basically after the first frame, everything is going to be fine anyway. So if I step forward, now we have a force, we come in here, and why is it not showing up? And none of these values are correct either. Okay, what's going on? There we go. Okay, I don't know what it was doing, but okay, frame 2, so we have our force, it's showing through, it's the same for every one of them, and we have the mass. Now from these values, what I really want is the acceleration. So everybody knows F equals ma, so force is mass times acceleration. So if we want to get acceleration, we want to divide our force by our mass. So we're just going to take our force and we're going to divide it by our mass. And this is basically telling us for a unit time how far is this piece expected to move based on the force it's experiencing. And that means we can get, I'm going to say PRJ pose for projected position, which is just going to be the current position, which actually, here's another problem. Yeah, I want this to work even if these pieces are moving. So if I have sort of a separated chunk that's moved away, so it's already broken off, but there's internal constraints, I still want those to be affected by fields. So I can't rely on this static rest position of the points that are stored in the constraints. So we do need to read one more value here. We need to read that position. So that's just going to get us the updated position of each of these points. So now our projected position is going to be that position plus this acceleration. And now in fact we don't need to store all of these attributes. We don't really need any of this stuff. All we want is this projected position. That's actually the only thing we really care about. So there we go. I had a lot of unnecessary stuff here. Let's get rid of all of that. Great. So now we have a projected position. So each of these points, again, it's not really updating right. If we move forward, there we go. We get this projected position of where it would expect these points to end up based on the force that they're experiencing. So now what we want to do is calculate something like strain. So this is going to be the equivalent of the impact that gets built up. So when you have a collision, when something strikes the object in bullet, it gets that little sort of collision force, that impact value, and that's the value that ultimately gets compared against some threshold, against strength, to determine whether or not the bond should break. So we want to do something similar with our sort of force effects. And the basic idea is that if two connected points, let's say we're looking at these 2 points, if these 2 points are experiencing the same force, then their projected positions are going to be the same distance apart as they were at rest length. So if they're both just moving, say, a little bit in this direction, then they'll be the same distance apart afterwards that they were before. There's no strain on that link. If two nearby points, or if two connected points, are experiencing different forces, say this one is being pulled up and this one is being pulled down, then the distance between them is going to get a lot longer than it was at the rest position. And that's kind of a strain. So the amount that these forces, even though they're not actually moving, we've calculated their projected new positions based on the force. We want to say how much longer is that than their resting. And that's going to be like our strain value. And we're going to compare that against some threshold to determine when we should break this. So now that we already have these projected positions, this is actually quite simple. All we need to do is grab our 2 points. So now we're running over primitives here. So we need to get those point attributes. So we're going to get this for our current primitive for point 0, and we'll do the same thing for point 1. And I just want those 2 projected position values. We're going to go vector PRJ. I'll just call it PRJ for projected. that's going to be 0.0 PRJ pose. And that's from PT0. And we'll do the same thing for our other point. Now we can set up a variable. We'll call this maybe force strain. And this is just going to be the distance between these two positions. Our projected position 0 and 1. So how far apart will they be if we were to apply the forces that are on them? And we're just going to divide that by rest length. Now you could subtract. Here I'm doing a ratio, and basically I only really care if it's larger. So if it's larger than 1, so I'm not going to worry about compression. You could have those as sort of independent values. You could also, if you did this as a subtraction, you would have sort of an absolute stretch away, which is also pretty common. So this is pretty arbitrary. What I will say, if you're setting up your constraints and they're going to switch to, say, hard constraints or soft constraints, then probably you've collapsed your points and uniqued them, and so your rest length is actually going to be 0. So make sure if you do go to that kind of a model that you sort of change this. Probably a subtraction in that case would make the most sense. How far away in absolute terms is it? Here I do want it to be a ratio, because if points are already pretty far apart, so if they have sort of a long constraint between them, then that sort of difference, you know, those forces could kind of pull them apart more in proportion, or I guess when they're close together, I should say, those forces are going to pull on them harder than if they were farther apart. And I want to be able to sort of respect that. So I like using this ratio here. Okay, so now that we have this force strain, all we need to do is compare that against some threshold. So we want to just say, if force strain is greater than some threshold, we're going to remove that primitive. And we'll remove its points as well. That'll only remove these points if they're not included in another primitive. So basically, once we've removed all the points that are related to one of these things, it's going to, I'll talk about this in a second, but it's going to get rid of those points at that point. So everything disappeared here. That's because our threshold by default is 0. So the strain is certainly greater than 0, or at least it's equal to 0. So let's just bring this up to some real value. And now everything comes back here. So at this point, and we can just drop, say, an output here, just to be safe. At this point, hypothetically, we've got this set up, and it should maybe work. But what we should see, and it's upset because it cooked sort of while we were inside there. What we should see here, though, actually, is that nothing really will happen. So if we step forward here, we have a couple of pieces that did come loose. And that's a little bit surprising. I am kind of curious about those pieces because all of them are experiencing the same force. And that's right. I guess if it's a much lighter piece, then it should be accelerated more. So yeah, what we're doing is we're losing light pieces that are attached to very heavy pieces. So even with a totally uniform force, like we're applying here, you should start to get some effects here that you wouldn't get by default. But it's not really giving us a lot. So if we really want to see some impacts here, what we want to do is make sure that our force is actually variable. It should be different. It should be, say, pulling different things apart. If we're just looking at like a straight push, ultimately that's never going to do very much. And if you really wanted it to come away, I suppose what you would say is that these inactive pieces are experiencing 0 force. And so if we were to just throw down a pop wrangle here, and say our group should be, well, let's just say if I at active is 0, then our force should also be 0. And if we do this, we're basically sort of reflecting the fact that these bottom pieces can never move. This is basically all that should happen for a uniform force. It should just break off, hopefully, at the top. And it doesn't seem like it's doing that because maybe the strain is just not high enough. Let's take a look at that geometry. Let's just go over to our constraint network. Where are we? Constraint network, our geometry. And get those out of here. There we go. Yeah, so we're getting some strain here. And actually, if we just come out here and look at this more straightforwardly, I'm going to quickly split these out, and just bear with me for a moment. I just want to link these up. I have a good reason for this, I promise. And we'll call this 2 and 2. Basically what I want to do here, I want to have an object merge. It's going to be here, and I want to just drag this over. So I'm just going to grab this and throw that right into there, and this will do the whole path for me, including this weird sort of colon and all these, like, you know, it's a long path. I didn't want to write that. Good chances I'd make mistakes. It's easier to just do this split. I don't need these panes anymore. That's really all I wanted it for. But now we should be able to take a look at our constraints, and really I want to visualize that force strain. And so what we can see is we are getting sort of good strain along the bottom, and we have already sort of broken a lot of those chunks down there, but maybe it's just a little bit too strong. So let's just change our threshold here. Let's just drop it down to maybe half that. And now we should see, yeah, it's going to snap pretty much all along the bottom here. And if we take a look, it's just going to snap straight off of those pieces. Yeah. Now this was strictly for sort of demonstration value. I just wanted to sort of point out that if all you're doing is a totally uniform force, you shouldn't really see very much. And physically you shouldn't really see very much because all of the different pieces are experiencing the same thing. There's not much strain between them. So really all that would happen if this stuff was locked to the ground is that it wouldn't be able to move, but the stuff above it would, so you would just snap it off like a hinge. But that's not terribly interesting. So all of that is to say, what we want to do if we want to see anything interesting is get a little bit of variation in here. And we can do this with a bit of noise. So I'm actually just going to give ourselves a good chunk of noise and maybe scale down that force up there. Swirl size of 1 is probably pretty reasonable. That's kind of this scale. Maybe actually I'll bump that up. That'll give us some sort of nice oscillations. And now what we should see is this whole thing will probably come apart. So a lot more pieces are coming apart there. Whole chunks are sort of pulling out. And we're starting to see a lot of these pieces are breaking. So if we let this run, we'll see that we're basically losing sort of all of these pieces. They're kind of just falling out as they start to detach. And basically it's just going to be the lighter and lighter pieces are going to be sort of pulled apart. And if we were to sort of bump this up a little bit more, so if we took our sort of noise amplitude up even higher, we should see the whole thing pretty much just rupture apart. And you can sort of see it's following a little bit of those shapes there. And with noise, we don't even need this base force necessarily, so we don't need any particular direction. We could just put this all into noise, and it's basically going to push and pull this structure in different directions and just tear it apart. Okay, so we're getting somewhere here, but this is pretty boring. We're getting it to respond to the noise, but we're not really getting any sort of terribly interesting things going on here. And there's a couple things I want to do to improve this. First of all, let's talk about the constraints. And so this actually is completely sort of independent of this sort of force breaking we're doing. This is the type of thing you want to do for any of your destruction sims, but we want to get a little bit of sort of chunking in here. So right now, every one of our constraints has exactly the same strength. It's not going to do anything very interesting at all. If you use the RBD material fracture, and even just setting it down without giving it anything to fracture, it takes it a second to sort of get itself in there. You can give it multiple levels. You can basically do hierarchical fractures, and under the constraint tabs, you can even have sort of level multipliers. And what this will do is basically say constraints, the strongest constraints, or rather the weakest constraints will have this value, and for each level that you go up, they'll get stronger and stronger. So basically large pieces will come apart sooner than smaller pieces. I don't often like using this. It's got a lot of nice features, but I find it really slow and also a little bit opaque, so it determines exactly how it wants things to work, and we can do something very similar on our own here. So what I want to do is take this same offset we used up here. So maybe I'll actually pull that over here. Leave this over for that fracture. What I want to do is basically just define some points that are going to be the centers of clusters at various different levels. And we can do this with just a few extra scatters. So let's do maybe 3 levels. So I'm just going to grab 3 scatters here. And the idea is this scatter is going to define my pieces, my most coarse pieces. And so we don't want anywhere near this many. I want relatively few, maybe something as low as sort of 16. Maybe even, let's drop it even lower, let's say like 12. So I want 12 chunks. I actually don't want them relaxed. I want them to have a little bit more variance. Maybe I'll give it sort of one iteration of relaxation. So I want these sort of something like that. At my next level up, what I want to say is, well, there's 12 main chunks. Each of those chunks, how many sort of medium chunks do I want to split into? And in general, I like sort of 3. That'll give me some variance. It'll be anywhere probably from 2 to sort of 4 in there. So I would take this and multiply it by 3. So let's just say 36 at that level. I'm not going to relax it. I'm going to change the seed. It's not really necessary because it's a different number, but that's okay. And then for my next level, we're going to sort of split even more, and we'll say, 36 times 3, that's somewhere around, let's just do 120. So we'll bulk it up a little bit higher. And again, we're not going to relax that, and we'll change this seed a little bit. So this is going to give us 3 levels of clustering here. And yeah, so let's start with that. And the way that I want to handle this, I think I actually want these, I want to flip them around. So I'm going to go from coarse to fine. And what I'm going to do, so just bear with me for a minute here. This first one is going to seem like a whole lot of extra stuff that seems totally unnecessary, but I'm going to do it for a good reason. And actually the first one doesn't need to, there we go, here we go. What I want to do is basically say for each of these points at the medium level, which coarse chunk are they a part of? And then I'll say for the finer level, which of these medium chunks is a part of, and that'll include the information about which coarse chunk it is. And the way I want to set this up is so that if I want to add a level, all I really need to do is just copy one node and sort of just pipe it into the chain here. In principle, you could do this with a loop, but you get a bit more control by being able to set each individual level, and you're probably not going to want to go much past 4 or sort of 5 levels, so it's not too cumbersome. So what do we want to do here? Well, first I want to figure out what is the closest point here. So I'll say npt for near point, and we just want the nearest point from that stream to our current position. Now I'm going to define a little array here. I'm going to call it cluster, and I'm going to set it to size 1, just one element, and then I'm going to set its first element to that near point. And then I'm just going to say I want this attribute value to be on my point. So once I've done this, if we look at our points here, you should see each of them has sort of a one element array, and it has values ranging from, they don't sort nicely when they're in an array, but basically it has values up to 11, and they should go down to 0 somewhere. It's possible none of them were the closest point to point 0. Let's just take a look at these. Some point numbers, point 0 was up there, and these points are all around here. Yeah, sure enough, all of these points are going to be closer to some of these. So that just happened by chance. We're basically only getting 11 major chunks, and that's fine. I don't really mind that. Now, at this stage, it doesn't really matter that this is an array. I should also note you can get arrays of any of these attributes with the normal @ declaration by just putting the square brackets after it. So I square brackets @ tells me this is an attribute type of an integer array. So at the first level, we're basically just generating this sort of single leveled array. When we move to our second level though, what I actually want to do here is instead of defining this cluster here, I'm going to grab it. I'm going to say, well, I will define it here, but I'm going to grab it from this near point. So I'm going to say it's going to equal 0.1 cluster at that near point. So at this secondary level, what I'm saying is, well, for these fine resolution points, what's the nearest medium one? Grab its cluster array, which is going to tell me right now what the coarsest value was, We're going to resize it to make it 1 bigger, so its current length plus 1. And then we're going to add that near point to the last position. So instead of into 0, we'll put it in whatever the last position is. And so now our first entry is the index for the coarsest chunk, and our second entry is the index for the medium chunk. And the idea with these sort of hierarchical constraints is you can then go through and say, if they have different clusters in the first number, then that's the weakest possible type of link. Those are links between large-scale clusters. If they have the same value, so if they're both 9, for example, then both of these fine scale points are within the same large cluster, and then we look at the medium one. If the medium one is different, so these two, for example, so they have the same large cluster, but they have different medium clusters, that means they should break sort of at an intermediate level. If they have the same large structure and the same medium structure, then they should be sort of the strongest links. And so we sort of move kind of down the chain in this way. And the nice thing here is that after we set up this first node where we make the cluster in the first place, these two nodes, you can copy them basically as many times as you like. So maybe actually instead of 3 levels, we want 4 levels. So we'll just grab these two values, and we just chain it on through, and say at this scale, let's get even more points in here as our base. Let's say 400. And now we have 3 different values. And so what we then finally do is go down to our actual constraint network here. Let me move some of these things. And we just want to ask for each of these points. So natural blur, that's not what I want. I want an attribute wrangle. For each of these actual points, let's just go ahead and get that information from our clusters. And so we'll use that same code to begin with. And now what we can do is go through and ask on each of our primitives. We're going to get its 2 points, so each point now on this primitive has this sort of array that tells it sort of what was its coarsest, its medium fine, its fine chunk. We basically get all these different levels of chunks. And what we can do for each primitive is figure out, well, what's the sort of highest level we get to before they're different. And that's going to tell us the strength that this attribute should be. So if that's our goal, what we're going to want to do is get those 2 cluster arrays. So this should be familiar by now. We just want to get our 2 points, our point 0 and our point 1, point, prim point, at primnum 1. So here are our 2 points, and we just want to get those cluster values. So let's say cluster 0 is going to be point 0, cluster pt0, and we'll do the same thing for our clusters 1. And we're going to get some level value. So I'll call this stren LVL for strength level. And by default, I'm going to set this to the length of one of these clusters. That's going to be the highest value we're allowed to have. That's basically saying it's the same in each individual thing. Most of the time, that's not going to be the strength we're going to use, though. We're going to calculate that here. So we're going to go through these arrays. So we're going to iterate. Oops, not int. This should be a for loop. So for each element in these clusters, and they should have the same length. They're always going to have the same length, so we don't have to worry about that. We can just check against cluster 0 or cluster 1. For each of these, we basically just want to say if the ith level of cluster 0 does not equal the ith level of cluster 1. So if they're different, this is what we really want to isolate here. We're just going to say then our stren level is I, and we want to break. We want to stop searching. So because these are ordered from coarsest chunk to finest chunk, we basically step through this array. And if they don't match the coarsest chunk, so if they don't match here, then this is our weakest possible one. So it'll get a value of 0 because it'll be the first one they check. And then it'll go to index 1 and it'll compare these. It'll only do that if it hasn't already broken out. And if these are different, then it'll get a value of 1. And so as we go up, basically if you hit the end and you've never reached this condition, then it just defaults to this, which is the strongest possible level. So if we then just assign that to our primitive, now we'll have all of these values that should be ranging from 4 all the way down to 0. And if we visualize these, put this on primitives, I'm going to do a ramp from attribute. The attribute is strand level, and it goes from 0 to 4. Here you can see our coarsest chunks, so you can see basically the boundaries between those are in black here. If we go up a level, you'll see the boundaries between our next level of chunks, and our next level of chunks, and our next level of chunks until we're at our sort of strongest chunks are all that's left here in white. So you can see that that works pretty nicely. We get this nice sort of really big chunks fading into smaller and smaller chunks. Now, this value itself, this strand level, is not going to change anything. What we want to do now is basically drive our actual strength. So we could do this on glue as well if we wanted to, but for now I'm just going to sort of put it, oh, actually I will. I'll put it on both glue and on our sort of break threshold. So what we would do now is take that strength value and use it to modify our strength here. And we want it to be relatively weak when it's between big chunks and very strong when it's between these sort of like within the very finest chunks. So I'm going to set this up with a sort of complicated expression, but it's nice and generalizable. So I'm going to say min strength, and I'll call this, we'll give this a parameter here. So this will be our minimum strength. And so I want to set our strength. I'll get a couple more parameters in here, but basically I want it to be the minimum strength times I want to sort of explain this before I write the whole expression. Basically what I would do is something like this, which is basically saying, well, let's take our minimum strength and then we're going to multiply it by 2 to the power of whatever our strength level is. So if our strength level is 0, this is just multiplied by 1, 2 to the power of 0, or anything to the power of 0 is 1. So this would just be the minimum strength, and then if it was level 1, then we would multiply by 2. If it was level 2, we would multiply by 4, and so on and so forth. So if we change this value, if we make it 1.1, let me set up a minimum strength here that's not 0, say 10, then you can see our strength ranges sort of not all that high. If I put 2 here, you'll see that it keeps doubling, so it starts as 10 and goes up to 160. If I put 10, for example, we would get powers of 10. So this is the general way that this works. What I want to do actually here, though, is instead of just specifying a single value, I often find when I'm doing these sort of hierarchical constraints, I want the first few levels to be closely spaced, and then I want them to even get stronger and stronger after that. So what I'm going to do here is basically, I'm going to replace this value with something a little bit more tunable. So I'm going to do a fit 01, and we're going to see where we're getting that range from, but then we'll go to, I'll get a couple more floats here. Let's say min base and max base. This isn't going to be happy because I haven't put something in the front part here. And then for this, I'm actually going to put a ramp, and I'm going to say, I'll call this strand base ramp, and I'm going to pass it basically scaled strength level. So we're going to pass in strand level. We know it ranges from 0 to 4. We could proceduralize this, but I'm not going to worry about that, and we're just going to move it into the value 0 to 1. Okay, so like I said, big ugly expression. What on earth are we doing here? The idea is, as we range from 0 to 4, from our weakest to our strongest constraints, we're going to be scaling this multiplier, the base that we are sort of putting into our exponential. We're going to sort of ramp that. So if we went from, say, 2 to 10, what this is saying is that when we're sort of near 0, when we're at our weak values like 0 and 1, we're going to be going sort of up in powers of 2, more or less. As we get towards our sort of strongest constraints, then we're actually going to be increasing those as powers of 10. And you know, you can control this ramp however you like. You could keep it as sort of 2 up until you could make it like a step. So at a certain point, they're doubling below, and then they're sort of tenfold above. So if I just set our initial as 1, we scroll through here, we start at 1, and then we go to 2, and then to 4, and then all of a sudden instead we're jumping up to 1,000. So now we're going up in powers of 10 all the way at the end there. And if we made this sort of a smoother ramp, then we would see we start at 1, and then we go up to 4, because I guess by the time we're at this value here, we're already up a little bit. And then 36, 512. Basically, they're getting larger and larger as they get stronger and stronger. So if you don't understand this, it's not a big deal. You can just basically replace this with a single base that you're interested in. This works just as well, and honestly, you're not often going to notice this difference, but I do like to do this because I like the bigger chunks to come apart easily, and then I want the sort of farther out chunks to come apart much more sort of, it should get harder and harder. Okay. So we can set this up, and we can set this up for strength. And so for strength, let's just go back in here now and set this to 1, so we're setting it up entirely outside. So over here for strength, minimum strength of 1 is going to be way too weak. And in fact, strength is going to be for impact, so I want this stuff to be pretty strong. And so let's do something like this. So we're going to have a minimum strength of at least 100, and it's going to go up to about 1,000,000 for those really tough pieces. So this stuff is not going to come apart strictly through impacts. And we might want to tweak that, but that's just fine for me for now. What we really care about is actually setting up our break thresholds for those forces. So let's just go ahead and grab all of this stuff, and we'll duplicate it down here, if it can let me get to a new line. There we go. We're going to need to rename all this stuff. So this will be, I'll say min. Maybe I'll just put an F in there for strength. I'll put an F here. F strength base ramp. F base, F base, F, and then I'm going to call this force strength. So now we should get a whole new set of variables down here. There we go. And in general, we'll need to dial this in, so I'll just sort of set up some numbers here and we'll see how nicely it works. I'm going to say as a minimum strength, maybe like 8. And we'll let it sort of grow slowly up to, yeah. In general, because these are ratios and they're going to be getting pulled apart pretty quickly, we don't need really high values like we have for our glue strength. We want these to be relatively lower. So we'll see how this works. This might be all right. And so now the last thing we want to do is go back into our SOP solver and actually respect those values. So instead of comparing against this threshold, now each of these constraints has an actual value for strength, and that's what we want to compare against. So we can get rid of this thing. We'll go to more and delete spare parameter. Okay, so with that all in place, we should get slightly more interesting behavior now. We're going to be sort of still just driving by noise, so let's just see what happens here. Okay. So if we look at our sort of force strain and our force strength, we can see that, you know, the strain is getting pretty high. We are definitely, if we look at just these, and we visualize our force strain again, I want to get the color off of here, and this just hasn't updated. There we go. We're definitely losing a lot of chunks in here, actually. You can see that it is breaking apart, so we've lost basically all of the connections between those intermediate ones, but we haven't quite lost enough for this to change, unless it just hasn't been updating. Yeah, so these are still maybe a little bit too strong, so that's easy enough to change. Let's maybe just drop our minimum and our multipliers there. And we're having a couple pieces coming off, and here we go. So we are actually starting to see it coming apart a little bit. So this is still a little bit too strong, but we are starting to see these pieces coming apart. So probably if we just amped up this noise just a little bit more, even more, let's just make it crazy. And here we go. It's really starting to sort of come apart at these seams. Because we're just giving it sort of noise, it's kind of being jostled back and forth a little bit, so it's not quite tumbling just yet. But we are seeing these nice things where we're getting these bigger pieces coming off and these littler pieces, and you can see that all these major cracks are developing along sort of the boundaries of those major chunks that we've defined. And you know, these aren't very interesting shapes because we didn't give very much resolution to this. We didn't do any kind of edge noise or edge detail. So this is a very trivial fracture, but it's showing a general workflow for getting these nice clusters here. And so if we actually give it a little bit of direction as well, we should really see it kind of come apart. And finally at around sort of 240, we're actually starting to see it really push through. And you know, this means we probably want to, let me just fix my display here. This means we would probably want to tweak these values. That was a little bit of a slow burn to get to this stage here, but if we let that sort of keep running a little bit farther, what it is showing that I really like is that this builds. So this isn't like an impact where it just sort of hits at one point. We're really kind of feeling it sort of growing, this pressure. And we actually aren't building up this force, but what we are doing is successively sort of breaking pieces and allowing this stuff to move more and more. And the more that it can start to move apart, the more it's being subjected to different forces, the more we're actually starting to get some impacts between pieces. And so this sort of strain on the overall structure really does start to build up over time. And now that it's snapped there, we should be able to see that it'll really just come straight down here. And that's what I really like to see here. If I get rid of these guides, I don't really need to see that. We're getting these kind of nice pieces. So again, even though this is a really trivial fracture that we did, a really trivial geometry, we're starting to get pieces that still have like bits of the floor on them. We're getting these really nice big chunks that are coming apart. And when that whole top level comes off, it's really coming mostly as one piece, and it starts to sort of fracture along those lines. And you can see how just by getting these sort of basic clusters, you can get some relatively interesting dynamics and shapes here. Okay, so there's a couple more things I want to do here, but we're basically done at this point. You can see that it works. We're getting sort of a force, and all we have to do is pipe some kind of a force into this terminal. As long as it exists on each of these points, this general workflow will function. But the other thing that I want to do is make this a little bit more like actual glue constraints, because we have these sort of properties here. We have half-life and propagation iterations. And basically what happens with these two things is that strain or impact, whatever the force is that's going to break this constraint, it gets calculated every frame, and then it decays. And so basically you calculate new strain, you add it to the old value, and then you decay over time. And this means you can have multiple small impacts build up into a large value. As long as they happen back to back fast enough that they don't decay faster, then they'll sort of build up and break in that way. So you can have one very large focal impact, or you can have a bunch of really closely spaced smaller impacts. And that decay is regulated by half-life. This is in seconds. And so this is how many seconds does it take for the value that's accumulated to reach 1/2 of its current value. So 0.1 is relatively rapid decay. We'll see with force, it's often nice to bump this up even farther. But the other thing we're going to want to implement is this propagation iterations. And what this does is basically spreads the force through the constraint network. And so if you get an impact on one particular point, propagation iterations, if it's at 1, that's basically all that will happen. But if you bring this up higher, and if you're using glue in general, I recommend using this. But basically if you get an impact in one spot, that force will spread out. It'll sort of blur into the whole network. And this gives kind of a smoother appearance and behavior. So what we want to do is set up these values for our network. So let's just go ahead and make a couple parameters here. I'm going to give them a new folder right at the top here, and we're just going to drop 2 values in here. And the first one will be our half-life, and the second one will be propagation iterations. So I'm going to set our half-life to something like 0.2, and let's just say propagation iterations of 4. Now we'll dive in, and we want to sort of take care of these two things. So first we'll deal with decay, and we'll do that before we do anything else. So we'll do that in a primitive wrangle. I'll call this decay. And basically what we want to do is get this value, this force strain value, is what we want to decay. So first we need to know how much time has elapsed since the last step. I find the built-in timing, I find this sort of unreliable, in part because if you have sort of different solvers working at different rates, you can't necessarily depend on this being correct in context. Usually it's right, but just for the sake of being absolutely sure, I'm going to do it a little bit differently. And I'm just going to say elapsed is our current time minus another variable that we'll have, which is called last time. And then after we do whatever we do for decay, we'll just set our last time to our current time. So this just lets me know that, okay, every time I pass through here, I'm going to figure out how much time has passed since my last sort of step. I'll take care of that myself. We can call this a sort of more memory-heavy version because we do have to store this extra variable, but ultimately in the context of a bullet network, one floating point attribute, not really a big deal. We've got plenty of others that we've added here already. So with elapsed, all we want to do is basically multiply our current force strain by 1/2 raised to the power of elapsed divided by our half-life. So this is basically saying how much of our half-life has transpired, and we want to do sort of 1/2 times that. So basically if the entire half-life had elapsed, this exponent would be 1. That means this would evaluate to 1/2. That means we would multiply our current strain by 1/2. When this is less than half-life, this value gets smaller, or sort of it gets larger actually, and so we're not decaying this by nearly as much per step, but after elapsed has reached, then we'll have done that amount. So basically this is just what lets us sort of, no matter what time has elapsed, we figure out how much we should decay our strain by, so that after a period of half-life, if nothing else had happened, it would decay to 1/2 of its original value. So for half-life, we just want to grab that parameter we set up. So that was up here. I'll just copy that parameter. I'm going to paste it in here so it doesn't break anything. Pull it back out, and we'll just put that right in there. So that takes care of decay. So basically before we do anything else, we're just going to decay this force strain. That means at this point, what we actually want to do is add it. And so instead of sort of just resetting it every time, we want to actually add it. We want to let it sort of build up over time. This is going to mean that we want to change our strengths probably, because the more that we let this build up, even if these forces aren't changing, then as long as sort of our time step isn't decaying it fully, they're going to sort of keep getting stronger and stronger. So we're probably going to want to tweak our strengths. But it does mean that we'll allow it to sort of build up and over time be able to accumulate. Now the other thing we want to do is that propagation iteration, and I'm going to do this in a really sort of straightforward way. I'm going to do it for each number. I don't even need this metadata here. And the number of iterations we want to do is going to be this value. Paste that in here. So 4 times we're going to do something. What do we want to do? Well, basically we want to blur these values. And there's a lot of different ways we can do this. I'm just going to do it with 2 attribute promotes. So first, I'm going to take this value, force strain, and I'm going to promote it from primitive to point. So that's going to, for each point now, is going to get a value that's the average of the force strains on all the primitives that it's associated with. And then I'm just going to promote that back onto the primitives. Force strain. Make sure that's the right name. It's always called force strain. That should go at the end. So basically, each time we go through, we're pretty much just averaging. We're going to average it onto the points and then average it back onto the primitives. And the overall effect will be that each pass we basically spread out that force, that sort of strain, across the network. And then once we've done all of that, at the very end, we'll go break constraints here. So this is our propagation iterations. There's our break. This is our, we'll say measure acceleration. And we'll call this update strain. There we go. We'll get this nice and labeled. So now, if we just go back and look at our network here, fix our display again. There we go. Now as we step through, okay, everything is gone basically immediately. So as I said, it's going to need to be a little bit stronger here. So let's just set our base strength. In fact, I'm going to set it quite high because I just want to show you what's going on here first. So that's pretty high. Are we visualizing anything? No. Here we go. So we have a little bit of force there. Already this is going sort of way too strong still. So this strain, I think because this wind is really strong, if you're just relying on instantaneous strain snapping these things, then you need really strong forces. Once you start letting the force accumulate, especially with sort of a long half-life and a lot of blurring iterations, you really don't need these strong values anymore. So especially this noise amplitude, that's way more than we need. Let's just bring all of this stuff down. So now we can start to see that it's really sort of fading in over time. Oops. And it's really kind of going very slowly for some reason. Okay, so I crashed my Houdini, and the reason is relatively clear here. On this propagation iteration, what I did was merge each iteration. And basically that meant every time we went through, we just blurred it once, and then we basically at the end, we're going to get 4 times as many constraints as we started with. And then the second time we pass through this, we're going to do that again. And so we very rapidly ended up with thousands and thousands of constraints. Before I sort of exited it on step 7, I was using about 28 gigs of RAM. So yeah, make sure to set this to feedback iteration, each iteration. So that's just going to say, once we finish this and go to our next pass, we're just going to take the output and pump that back in. So yeah, that's pretty important. So feedback each iteration. Okay, so this should behave a little bit better now. We'll go back to auto update. And it's possible some of those strength changes I made, well, we'll see how many are even still here. Did I change any of this? Okay, we're back at our original values now. The display is already messed up. There we go. And we want to see force strain. Okay, so now what we should see as we step through, okay, they're much too weak. And we determined that before. So let's just do those things again. So again, we have just way too much of all of this stuff. I'm going to bring this stuff way down. And I'm going to bump up these strengths. So now as we step through, we're again breaking pretty early. Our strain on here is coming up pretty quick. But you can start to see that it's sort of smoothly kind of blurring and ramping up in here. So if we make this a bit stronger again, and actually let's just make this very strong so it shouldn't break, what we should see, yeah, now you can see the general idea here. These values are sort of bumping up, and this is going to sort of auto scale the range. So let me just clamp this to something. Let's give it a min and a max. Let's go from something low like 10 up to say 500, maybe even like 300. That should be fine. So what you can see is very quickly we get these hot spots, but they also really blur and spread through the network. So you can see that blurring there now. Once we give this a sort of a scale to work with, you can see that's really spreading through across each of those iterations. And that's what's going to let this sort of start to break a little bit more smoothly. Now this is ramping up really, really quickly. Basically we're going from nothing, and in a few frames of this blurring, we're getting all the way up into sort of huge values. So I'm going to want to scale this down a little bit, and what I'll do is basically get our strength more in that range. And so actually, if our strengths are ranging from 1,000, this might not be so bad if our sort of force is getting up into sort of those levels. Let's just see what this is looking like. So we are losing primitives, but apparently we're not doing it fast enough for much of anything to happen, although this is getting pretty close. You can see a lot of this stuff is gone already. I'm going to let it do it automatically again. So if we let this run a little bit farther, possibly we've sort of tapped out the strength of that noise a bit. Give it a little bit more local variation there. And there we go. Over time, that's sort of starting to build up. And so if we dial in some of these values, we've reached sort of a plateau. So if we let it decay a little bit more slowly, give it some extra iterations here, we should really start to see it coming apart sooner. It looks like potentially what's happening is that this force is just not pushing these pieces hard enough to actually knock them over, although it is starting to bend a little bit. We're getting a lot of sort of resistance there. I might even bump this up a little bit higher, just really let it start to break through there. And I'm going to take this back down. This down a little bit. I do want it to come apart. I don't want it to be just the largest chunks. That sort of defeats the purpose of that hierarchy, so that's looking better. Nice. So now what we get is that we get this sort of gradual buildup of this strain. So we let it continue to keep adding into there and spreading through the network, so we get a more overall collapse. Whereas before we would get sort of these localized individual pieces, now we're getting that sort of strain spread out throughout the network. And maybe this is a little bit too much. You know, there's a lot of dialing in to get the look that you want. Obviously, you've seen from my many mistakes, I probably should have just tuned in some values earlier and pretended I got them first shot. But you can see the sort of general workflow for how you can tweak some of this stuff and figure out sort of how to get the look that you want. Okay, so to close off, I just want to show you that basically you can put anything you like in over here. So here I just used a basic pop force, but let's do something a little bit more interesting. Let's give it a little bit of a curve force, just to show that you can really sort of respond to some more interesting effects. So I'm going to get rid of that pop force, and I'm going to drop in a pop curve force. And what we're going to do with this is we're going to feed it in a curve, and we'll be able to tune a few different values there. So let's just jump out here and make ourselves a curve. I'm going to template my geometry, and I'm going to do a draw curve. I want to draw this. I'm going to project it onto the ground initially. I'll go to ZX. I'm going to go to my top view. And we'll just use this, and let's say, how do I want this to work? Maybe I want it to kind of come, no, I don't like that. Hang on. Do that. I'm going to get it to sort of come through here, and then back through and up in this kind of a direction. That should do. I'm going to resample this. And I'm going to make sure I have my curve view on here. And I might transform this to give it a bit of a different position. I maybe want it to loop like right around the building, sort of like this. Okay. And right now this is all just lying flat on the ground, but I grabbed that curve view for a reason, because what we can do is just say attribute wrangle, and we're going to say at p.y is fit01 ramp. We'll call this our height ramp. We're going to pass it curve view, and then we'll just get our min height and our max height. So if we create these and we just give ourselves some values here, let me just template that again. Minimum at 0 is probably fine. Our maximum we can start to scale up. We definitely want that higher, like 4, maybe even go up to 5 or so. Really get it sort of looping around. I kind of like this. So it's going to come in, curve around, and really sort of pull off some of these outer parts of the building here. That's looking pretty good. I think I kind of want to smooth this thing. Maybe I'll do that after I've given it its height. That's a little better. Okay, so that's good enough for a shape. We don't really need to labor this too much right now. So I'm going to call this my force curve, and we'll go back into dops, and we're just going to pipe that in here. So we'll point to there with our SOP, turn off our point visualizer, and this is sort of what this pop force is going to do. So right now the radius is really, really wide here, so I'm going to change that onto this max influence radius. 1 is going to be starting to pull a lot of that. I might even want less than that. Let's really just bring it way down. I kind of want it to be really isolated to these parts where it's overlapping. So that's looking pretty good. Now what we want the force to do, we have a few different variables in pop curve force. So follow scale is basically how much is it going to go along this curve. Suction scale is how much is it going to be drawn towards the middle of the curve. And orbit scale is how much is it going to sort of rotate around here. So let's maybe get sort of a bit of all of those things, but the main thing I want is the follow scale. I want it to sort of get pulled and drawn up in this direction. So let's bring that up to maybe something like 4, and I'm going to leave these values the same. There's no velocity on these points, but I'm going to turn this off anyway. What this is saying is if there are any points on this curve that have velocity, so if our curve here had v values, then those would get sort of passed along, and they would be inherited onto the points that are influenced by it. So I don't actually want that. We're using this directly to produce force. Now with that in mind, with this value, treat as wind ticked off, that actually means it's not going to treat it as force. What it's going to do is instead of setting a force value, so actually if I just play through a couple frames here, you'll see nothing's going to happen, and that's because it's not setting force. So there's nothing here, none of these get anything. What it's setting is target V. And this is basically saying how fast do I want it to be. So that's how wind works. So if you were wondering what's the difference between wind and force, wind sets target velocity, which is what the points try to match, and then air resistance is what creates sort of drag. Forces set the force property. So we want this to be a force thing. So if we untick that, now we get forces here, and we untick ignore mass so that we get sort of uniform forces. So now if we turn this on, we should start to see, we might have to dial in these strengths a little bit more. Yeah, that's not going to be quite enough. Take a look at this. We are seeing we're getting this strain and we're getting it breaking exclusively in these spots here. It's just not quite doing enough yet for us to see anything. So let's go ahead and dial some of these up. Let's say bring this to 6, maybe 1.5 and 2. We'll give it a nice sort of twist. I'm not sure what sort of scale this is supposed to be on. It doesn't actually visualize any of that curve, so this will do. And we're just starting to see some pieces coming off here, so this is spreading a little bit too slowly. It's not sort of giving us enough yet, so let's just keep boosting this. I'm going to be a little bit gentle about it. I might let Ooh, that's really high, that half-life. I'm going to drop that down again, but I'm going to get more iterations. So I'm going to blur it farther, and we're going to amp up that force, and we're just going to keep dialing this in until it does something that we like. Again, definitely too slow here. Let's just double all of these, and maybe let it influence a little bit farther, actually. So let me just see this shaping. So that's radius along length. Okay, so this is the fall off from curve. Okay, so what we can actually do is sort of set ourselves a little bit of a scale here. And so we can give ourselves a wider radius, but basically taper off the influence as we get towards the outside. I think that should be good. That'll influence more points, which will help this to drag more. So it's definitely breaking a lot of these pieces. It's just not quite drawing them along yet. Some of this could be actually that our glue is too strong. I'm going to maybe drop this down a fair amount. I know we made it really strong outside. Let me just sort of notch that down. Because part of what we might want is that once these pieces start to break, they can sort of jostle their neighboring pieces and cause some actual impact breaks as well. And here we're starting to see this stuff getting pulled through. Okay, so that's starting to work. One other thing I want to do here to get this to really show this field effect is I'm actually going to turn off gravity for now. And we're going to put it back in, but we'll put it back in a slightly different way. But I just want to show you we should get some better effects here because the force is going to really push this stuff a little bit more strongly. So right away we're seeing some of that stuff is getting pulled off more cleanly. I'm still not seeing what I'd like to down here, so let's just keep ramping this stuff up. I'm not really seeing, well, I'll keep a little of the orbit on, why not? So part of the problem here is that the force is, actually it shouldn't be. The force should be pushing it out of the building there a little bit, so we might just need to give it a little bit more time here. You can see these pieces are really struggling to sort of break free. I'm going to take a look at strength again. What did I do? Yeah, these are going to be truly extraordinary levels. Let's just go to 10 there as our weakest. I'm going to put this back to 1. That should be okay. I am going to give it some propagation iterations as well. And I'm going to pull up this half-life a little bit farther. This is starting to look good. What I really like about this actually is this slow build. So little pieces come off and then you see it starts to break. It starts to sort of weaken as more and more of these pieces are coming off. And I think, there we go, we're starting to get it from here. I think once this pulls away, we might start to see a little bit more movement here. We're going to get a little bit less resistance from these pieces trying to jostle. I think we're almost there. I'm going to pull this radius out a little bit farther again. And let's just really amp this again. There we go. There we go. Now we're finally getting those pieces coming out. That's really, I really wanted to see. I wanted to see that full sort of wrap around there. Okay, so this could obviously be tweaked a little bit more, but this is enough for just the very last thing that I want to do, which is to bring gravity back in. I really like that when you turn it off, you get a lot more of this sort of lift. You get these things actually sort of following this sort of force field, and that's a lot more interesting to me. I really like to sort of see that. I might even turn suction way on so it really sort of pulls into that area. But the problem here, of course, is that it then doesn't respect gravity. And so I feel like as a sort of, oh, that's looking real good now. I just need more suction, apparently. The problem here, of course, is once it escapes this field, then it just sort of drifts out into the ether. So what I want to do is basically apply gravity to any of the pieces that aren't being sort of affected by this force. Because obviously this force is almost like this would be like a sci-fi or a magical effect or something. It's not really governed by the laws of physics in the normal way. There's nothing we can really think of that would produce this kind of a shear on a building. So it's a very sort of specialized kind of approach. So it makes sense to maybe turn gravity off in that sense. It's like it's a force field or a traction beam that's sort of overriding gravity. But as soon as it's out of the influence of that, we do want gravity to then take effect in a normal way. So what I want to do for that is just a real quick pop wrangle. And what I want to say is I want a conditional with two things. First, if it's moving, so if the velocity is greater than 0, so I don't want to really apply gravity necessarily to stuff that's not moving at all. I don't want to worry about that too much. I want to leave that sort of for this force no matter what. So if it's moving and the force that we just calculated here, if that force is less than some very small value. Whoops. And we need to use our length again. So if those two things are true, if it's moving, but it's basically outside of the influence of this sort of pop curve force, then we're just going to say our force is equal to gravity. So 0, negative 9.81, and 0. So now we're going to set our force initially based on this, this pop curve, but then we'll say if our piece is moving, but it's not in the influence of there, then we'll just use gravity instead. And here, by just setting force to be gravity, that's basically identical to what we would do with that gravity force down there. So now, as these pieces come apart, you'll see once they leave, they seem to be just floating up into the sky. All right, clearly that is not working yet. Of course. Len is how many elements are in an array. So, 3 is greater than 0, so this will always evaluate to true. 3 is never going to be less than 0.05. This will always evaluate to false, because I'm not asking about the length of the vector. That would be the function length. So len is how long is an array, how many elements are in it. Length is the length of a vector. So there you go. Stupid mistakes. We all make them. Well, I certainly do. Okay. Now it comes through and yeah. So it is working now. You can see they're being sort of ejected with really high velocity. So they're actually kind of getting thrown out there pretty far. But they are coming down and hitting the ground afterwards. That's pretty good. So what I might also do in this case is maybe as soon as they leave that field, we can even sort of damp them a little bit. So let's just give it a little bit of drag, and we'll give it a little bit of angular drag as well. And there we go. So if we come back out here, so we're just seeing this geometry. There's a couple things I liked in the end there. So it sort of twists apart, and we're getting that kind of buckling there. I like this sort of motion. We're getting that twist here. So that's kind of fun. The other thing I really liked at the end, yeah, as it fell down, this piece here, you can see it sort of falls into that stream, gets carried along, and then ripped apart by those forces. So that's really fun. So overall, this is kind of the general approach, and it's really not so difficult. What we're doing is we're saying, well, what does glue do on its own? It accumulates these impulse values, and it actually has an attribute impulse. Once they start to hit each other, we should be able to see, actually, if we just go out here, sorry, not impulse, impact. So this isn't something that we produced at all. If you've done the dynamic fracturing tutorial, we'll have talked about that there. But this is a value that DOPS is producing for glue. And basically how glue works is when this value is higher than strength, then it breaks. So all we're doing is we're saying, well, let's make our own value that we treat that way. And what we did was we basically figured out, given the forces acting on these pieces, if they're getting pulled apart, then their projected positions are going to be farther apart than they are at rest. And we basically take the ratio between where we expect them to be and where they are, and we accumulate that value instead. And that allows us to get this sort of nice movement coming through here. So this is a pretty straightforward workflow, but it gives these nice effects, and it lets you do things. It gives you all the advantages of glue, which is to say it's really nice and fast, it's really nice and efficient, but you can still break it with forces. And you could use a pyro sort of velocity field, you could use that to drive your forces. Basically anything on this input that puts a force attribute on your points can be used for this effect. And if you don't want the force to actually act on it, if you just want a field to be breaking it, but if you want some other thing to drive how it moves and its dynamics, in that case all you would really want is to have some other property, because this doesn't need to be force. All we're doing with force here is we're using it to calculate acceleration. The solver itself respects this variable force, so if we put force on here, we can do, let's just say a pop wrangle. We can just set any force we like. We can just sort of set it straight in here. We could go -50. I guess this is going to have no noise on it. Let's just say times random at btnum. That's fine. Just something to show. If you put force on it, it will respect that force. We don't need to use force here though. So what we could do is take this whole curve thing we've got here. Let's just put this curve force back in here. I'm going to put a new pop wrangle. I'm going to say my force equals that force value, and then we'll reset force to nothing. And now we could go in here, and instead of using force, we'll just bring in that my force variable. And now this curve field will still break everything, but it won't. In fact, we have no forces acting at all, so let's just put gravity back in here for now. Now it's not going to get drawn along the curve, but it's still going to use that force to break it. So if we play this now, you're starting to see these breaks. It's really starting to fracture because of that force. But it's not going to be drawn along there at all. The only force it's experiencing is gravity. And this is part of why it's not really going anywhere. It's just waiting till it can fall out. And there you have it. Those chunks are sort of falling out. So I just wanted to illustrate that you don't need to use literally force. Basically, anything that produces a vector that can be treated as force, that can be thought of as force, can be used in here. If you want it to also be advected by that force, and I think that's probably usually the more typical sort of workflow, then it just makes sense to keep force. Just let it be named force. Just use that force as it exists. Get rid of gravity again, and just bring it in, and everything is sort of unified. And so whatever you pipe in here as the force is going to sort of respect for both braking and for movement in the solver. But if you do want it to just influence the braking and not the moving, then just use your own variable there instead of the sort of built-in force variable. So that's pretty much all I wanted to cover today. It's a relatively straightforward workflow, but I think it's one that can be pretty useful. We often want to use glue because it's so nice and cheap. It has really good properties, but the problem with glue is that it only really pays any attention to impacts. So if you want it to pay attention to something else, well, you have to build that in yourself. And this is just the way that I've approached that for things like fields. And the nice thing about this is it can respect sort of any arbitrary field, any arbitrary force, as long as you produce that force attribute or some other similar vector attribute, then you can get it to sort of behave just as you expect. And it's pretty easy to implement things like the half-life decay and the propagation iterations, and that overall just gives it a really nice sort of tunable effect. As always, let me know if you've enjoyed this, and especially if you sort of end up using this for anything, or if you have any sort of suggestions or questions or comments. Love to hear all of those. I'm going to be a little bit AWOL for a while. I'm actually moving internationally in just a couple of weeks, so I'm going to be without my workstation and pretty much disconnected for a little while. But stay tuned, I've got more stuff coming, and if you have anything that you're sort of looking to see, please do let me know. And as always, thank you very much, and goodbye.